Welcome back to Chem 4300. In this video, we're going to continue Chapter 4 on rotational motion, and now we're going to look at how you might go about diagonalizing a moment of inertia tensor that's not initially diagonal in your orientation that you've chosen. So in the previous problems we looked at, we always placed the molecule in such a way that the axes of symmetry, so like the threefold or higher axes, were along one of the coordinate axes, so along x, y, or z. And when you do that, generally speaking, then you have a much better chance that your tensor is going to come out diagonal with that orientation. But there are going to be cases where you can't identify any symmetry axes, and when you place that molecule in the coordinate system that you've chosen, then when you do the calculation, it's going to be non-diagonal, and you're going to have to do a diagonalization to figure out what are the orientation that actually diagonalizes that the tensor for that molecule. In other words, you want to find out what directions in your original coordinate system are associated with the principal axes system. And you also want to know what the principal component values are. So let's take a look at this example where we take a water molecule and we place it with now the OH bond along the z-axis. So this is not as clever as we did the first time. And when you do a calculation based on this orientation, then you get a moment of inertia tensor that's not diagonal. Now it's not so bad in this particular case. We have some zeros in here because that's because we placed the molecule in the xz plane. So we left it completely in that plane. If we had sort of tilted it out so that it also had a little bit on the y-axis, then we would have had a completely non-diagonal tensor here. But this is enough for us to sort of illustrate what we need in this section here. So now let's get to how we're going to go about doing this. Now you remember that the angular momentum vector is related to the angular velocity vector through this relationship here with the moment of inertia tensor. Now we're after the directions which are the principal axes of the moment of inertia tensor. So let's say that we defined our angular velocity vector so that it was pointing along the c direction of our moment of inertia tensor's principal axis system. So if that was the case, then when you did this multiplication, you would just get back IC times that angular velocity vector, which we've aligned intentionally along the c direction. Now, we could do the same with the other two directions. So I could align my angular velocity vector along A, and then when I multiply the tensor times that angular velocity vector, I'll get back the A value, principal component value. Similarly, if I did the same thing aligning it along B, I would get the B component value. So what we have then is we can take a look at this expression. I can rearrange it. First I'm going to divide by the magnitude of the velocity vector. It doesn't really matter that I use the angular velocity vector in this particular case here, but we divide it out and we see that what we get is this more general equation, which is that the moment of inertia tensor minus its principal component value times the identity matrix, which is just diagonal ones, times the unit vector along the direction of either A, B, or C. So this is going to be either EA, EB, or EC. So one of those principal component values. That gives us a set of simultaneous equations. This is a set of three simultaneous linear equations. Now, if we want to solve those, we know the way to do that is to write it out as a determinant. So what I'm going to do is take this equation, these three equations, write it out as a determinant, and if I expand that determinant, I'm going to get a third order polynomial in the principal component values, and the roots of this polynomial will be our three principal component values, IA, IB, and IC. So that's what we're going to do to get the principal component values. To get the orientation, then we'll go back to our equation. So this time we'll plug in EA, EB, and EC here, and we'll put in our values for IA, IB, and IC, and we're going to get a set of equations. This will give me three simultaneous equations, three simultaneous equations, and three simultaneous equations here. These equations will tell me the direction. I can use those equations to solve for the direction of EA, and here I can solve for the direction of EB, and here I'll solve for the direction of EC. Okay, so let's look at an example to make these ideas more concrete. So let's go back to our non-diagonal matrix, which is in this form, and I'm going to then set up a determinant. Now, so I'm going to take advantage of the fact that I know that these guys are zero here, so I'm going to set up the determinant like this, and I'm going to expand it out. I'm going to get this polynomial. And right away, you can see that one of the roots is going to be pretty obvious. We'll go to the next slide here. So that root is just that we're going to call I1, the first root, is just equal to IYY. And that one we know the value of that. That's 2.916 times 10 to the minus 47 meters squared kilogram. So that's one root out of the way, but now we need to get the other two roots. So we go back to this part of the equation, and this is the guy that we need to solve to get the other roots. So we're going to use the quadratic on this, and there'll be two solutions from the quadratic. You can work this out yourself here. There's a little bit of algebra involved, and you'll find that the solution for one of the other roots is 1.914 times 10 to the minus 47 meters squared kilogram, and then the other root, the last root here, is 1.002 times 10 to the minus 47 meters squared kilogram. So now we've solved for all the principal component values. We need to now assign them according to the convention. And remember, the largest one is going to be the C direction. So you see here the largest one, which was originally along IYY, which we're defining as the first one. We found as the first one is going to be the C direction. The next biggest one is this 1.914, so I2 now we're going to define as the B direction. And then the last one, the smallest one, is 1.002, so that's I3, which we'll define as being the one being along the A direction. Okay. So that's it for getting the principal component values. Let's look at how we're going to get the orientation. So we have this diagonal matrix now for the principal axis, for the tensor in the principal axis system. To find the orientation of EA, EB, and EC, then we need to take our original matrix and we're going to subtract out along the diagonal IA, and we're going to get a set of equations that we're going to solve to get the direction of EA. Okay. Now these equations that we get in this case are going to be redundant, so we won't be able to solve for exact values for the X, Y, and Z components of the vector, but we will be able to get a direction with some normalization. So let's take a look at how we do that. So let's start with the easiest one, the IC case. This was the largest component, and so we're going to put in 2.916 here into our matrix, and we're going to subtract it off the diagonal elements. We do that subtraction, we get this matrix, and that's going to be multiplied times the unit vector, which is now defined in our coordinate system. So we're going to have X, Y, and Z components for that unit vector in our original coordinate system, and we're going to get these two equations out of this result. We don't have one of the equations because there's all zeros here for the YC component. And so to get a solution for XC and ZC that satisfy this is actually trivial, because if we plug in XC equals 0 and ZC equals 0, then we get this satisfied. So put 0 here and 0 here, we get 0. 0 here and 0 here, get 0. So that's kind of a very trivial solution. But what it tells us is that really Y now, because these are the constraints that make this true, Y can take on any possible value. So this is a solution telling us that the solution is any point that lies along the y-axis here. Well, we already knew this anyway. We already knew that the molecule was sort of block diagonal, that all the y components were gone when we placed it in the xz plane. So what we're going to do is we'll just define then C as along the y direction. So this was the easy one. Now let's look at the other two, which are a little bit harder. So now for the B component, which was a value of 1.914, we subtract that from all the diagonal values. We get this matrix here. Now we'll multiply this out and we get three equations. And now we don't have such a trivial solution. So we can satisfy these equations by setting YB equal to 0, and we can set XB equal to 1, and then we can solve for ZB, and we get a value of 7.6644. So that allows us to create a vector. So using Y, X, and Z for those components for the vector, we can define a vector that is along EX with the value of 1, and along EZ with the value of 0.76644. And that points in the direction associated with IB. Now, we like to have our unit vectors normalized, so what I'll do is I'll take the length of this vector, which is x squared plus z squared, square root, and I'll evaluate 1 plus 1 squared plus 0.76644 squared, and I get 1.256. And after I take the square root, and then I'm going to divide by that to normalize, and then I get this value here. So now I've defined the b direction of the principal axis system in terms of the EZ and EX of our original coordinate system. That's a little bit harder than the previous example. Now the next example for A is about the same then. So now we got 1.002. Again, we subtract it from the diagonal. We get this matrix. We multiply it times the x, y, and z vector. We get these three equations. And now what we do, we set y equal to 0. We set x equal to 1. We solve for z. We get minus 1.30159. We can now construct a vector which points along the direction of the A principal component axis. And so now we have 1 times EX minus 1.30159 times EZ, and that's the vector it points along the direction. Now if we want to normalize it, we'll take the x component and the z component, we'll square them, take the square root, we get 1.614, and then we divide by that normalization factor, and we get this expression for EA in terms of EX and EZ. Right? So that's it then. We've solved for the directions. We got these three equations for EA, EB, and EC, and I can actually use these equations to draw those unit vectors. So here I've drawn EA, here I've drawn EB, and again EC is coming out of the board along the y direction. And as you look at this, you can see that that is pretty much in agreement with what we had seen before when we drew it more cleverly at the beginning of the chapter. Okay, so that's it for this short video on how to diagonalize a moment of inertia tensor.